Hello, good morning, everyone. I want to welcome you to another statistical theory class. I want to believe you're all hearing me, right? Everyone hearing me? Okay. Today we are starting a new chapter, chapter 3 from the textbook. I want to believe by now you have access to the electronic version of the textbook that I publish on Moodle, the course canvas. You can check that because the assignment for this week I actually extracted the assignment from the textbook. So today we're starting a new chapter, and we actually I'm gonna go over discrete random variables and their probability distributions. Okay, so discrete random variable and their probability distribution, of course, in the outline. I'm actually going to walk you through what we mean by discrete random variable. Then how do we figure out the expectation, the variance, and the standard deviation of discrete random variable. Then I'm also going to walk you through what I call linear combination of random variable. But because we actually want to, what is going to take a center stage today is random variable. We want to be able to understand the probability distribution associated with random variable. And not only that, because if we're able to have the understanding of the probability distribution associated with a random variable, of course, we'll be able to find the expectation, which is the average, the variance, and the standard deviation. So what do we mean uh, by variable itself? When I talk about variable, so what do I mean by that? Okay. Before going to random variable, so the question is, what do I mean by variable? Okay. What do I mean by variable? Because if you understand variable, you understand what we mean by random variable. Okay. By variable, we mean anything, okay, that is liable to change. Okay, anything that is liable to change is what we call variable. Your score is liable to change. Your temperature, the temperature changes, income changes, height changes, weight changes. Okay, anything that are liable to change. Of course, I told you the other time, we live in a probabilistic environment where you can't rule out variation. Now, what do we now mean by random variable? Okay, what do we mean by random variable? Now that you understand what a variable means, anything that is liable to change. A random variable is a mapping function, okay? A mapping function, a mapping function that assign numerical, that assign numerical values to the element, to the element in the sample space. Okay, the random variable is a mapping function. Of course, in this class, I've walked you through different kind of function. Okay, so it's a mapping function that assign, in when you perform experiment, we're actually going to have possibility, right? Possible outcomes, right? The possible outcome is the sample space. So when I assign, okay, numbers to elements in the sample space, then what actually help with that is random variable. Okay, the random variable help us with the assignment. If I toss a coin once, And in my sample space, I have head and tail. Then the random variable, if I want to define a random variable, okay, maybe I'm going to say the number of heads. Okay, now based on this, the numbers of heads, okay, could be 0, could be 1. Okay, now these are figures, these are numerical values. I'm assigning numerical values to the elements in the sample space. And what enabled me to achieve that is a random variable. So I'm trying to say, oh, since I've defined my x ahead of time, if x is numbers of heads, okay, here, head, then head equal to 0. Here, head equal to 1. That's what I mean by 0 and 1. Okay, so that is what random variable does. Now, away from that, we have two types of random variable. Okay, we have two types of random variable. We have discrete random variable. We have continuous random variable. When I talk about discrete random variable, I'm actually, today we're going to be focusing on discrete random variable. Okay. Now, when I talk about discrete random variable, okay, I actually mean, only a finite or a countably infinite numbers of distinct values. Maybe I want to talk about the number of students in this class. I want to talk about the numbers of goals scored in a soccer game. Okay, that's what I mean by discrete random variable. Now, I need you to pay attention. I can use X to denote a random variable. I can use Y. You can see right now, what am I using? I'm actually using Y. Okay, but if you want to denote a random variable, it has to be an uppercase letter. Okay, this is going to be wrong. Okay, if I use this guy, if I use this, that's wrong. Okay, you have to use an uppercase, okay, for random variable. Now we're focusing on discrete, so which means in a discrete random variable, what we're going to be doing, we're going to be assigning discrete values to elements in the sample space. That's exactly what we're going to be doing. Now, the next I want to talk about, I told you the other time when I was talking about probability space. Of course, in probability space, okay, in probability space, okay, we have a triplet. In probability space, we have a triplet. Okay, now I want to remind you of probability space. Okay, in probability space, okay, we have a triplet of this. Okay, now the first is the sample space collection of possible outcome. The second is calling F, that we call the set of events. The third is probability measure, which are assigned probability to events in the sample space. Now, what do we want to talk about now? We now want to talk about that probability. Okay, we want to talk about that probability. Okay, we have a random variable. Okay, we have a random variable y, which is discrete in nature. Okay, and we now want to figure out what is the probability associated with a discrete random variable. Okay, now that is exactly what I mean here. Okay, I want to find what is the probability associated with a particular outcome. Okay, when you take a look at what I have, that guy is trying to say, what is the probability that my random variable will actually take a realized value? Okay, a realized value. Like, what is the probability that my random variable is going to be 0? What is the probability that my random variable is going to be 1? That's exactly what I mean. So, which means for every random variable, okay, for every discrete random variable, we actually want to have a probability associated with that. Okay, that's what I mean. Now, now that's our motive. Okay, and that's how we write it. I needed to pay attention to all of this. Okay, we want to figure out the probability associated. Now we want to go into an example. A supervisor in a manufacturing plant has three men and three women working for him. Three men, three women working for him. He want to choose two workers for a special job. It's like he has a total of six people working for him, but he actually needed to choose only two, okay, workers for a special job. Okay, not wishing to show any biases in his selection, he decided to select two workers at random. It's like you want to give equal chance to everyone. Okay, actually want to eliminate what I call any favoritism or biasedness in the selection. Now, let Y denote the number of women in his selection. Okay, now I need you to pay attention. I need you to pay attention. We normally define our random variable. In this question now, okay, the question is already telling you what their random variable is. Okay, the random variable in this question may be different from random variable in another question. Right now, the random variable here is the number of women in his selection. The random variable could be the number of men in a selection. Okay, but right now, the focus of interest, the characteristics of interest is the numbers of women in his selection. And don't forget, how many people does he want to choose? You want to choose two, right? If I want to talk about numbers of women in the selection, it could be 0, it could be 1, it could be 2. Does that make sense? Because he's choosing two people. Okay, now what I'm going to do right now, I need you to pay attention. Okay, pay attention, like I said. Okay, now the very first thing I'm actually going to do is I need to first figure out what is my random variable here, because they said number of women and they actually want to choose two, right? They want to choose two people, and we want to know what would be the number of women in the selection. Now we need to first define our random variable. Okay, now take a look at this. If you take a look at this value, because of the fact that they are choosing two people, the number of women in the selection could be 0, could be 1, could be 2. If they are choosing three people, the number of women in the selection could be 0, 1, 2, 3. If they are choosing 4, 0, 1, 2, 3, 4. Does that make sense? Okay. Now, the next thing that we need to do is, because we want to find probability associated with this event, then we need to first figure out what is going to occupy the denominator position, okay, the denominator position in the probability. Now, we need to consider what is the possible numbers of ways of choosing two people out of 6. We normally use this when we can choose anybody. We want to choose two people. We're giving equal chance to everyone. Then we're going to do 6 combination 2. 6 combination 2 is going to give us 15 ways. There are 15 ways, of choosing two people out of 6. Now, let me tell you this. If we have 15 ways, okay, it's not going to choose 15 ways. It's only going to choose one out of the 15 ways. If it's going to choose one out of the 15, then the probability for each is going to be 1 over 15. The probability for E1 is 1 over 15. For E2 is 1 over 15. Up to E15 is going to be 1 over 15. Where do I get 15? 15 is the possible numbers of ways of choosing 2 out of 6. In such a way, we're using combination. Has anybody heard about combinatorial analysis? Okay, that's what we use here. Now, do you not know what I want to do right now? What I actually want to do, I want to find probability associated with my random variable. Now, right here, this is probability associated with events, choosing one of the ways out of 15 ways. But that is not what I'm looking for. I'm actually looking for what is the probability of choosing zero, of choosing one woman, and of choosing two women. Okay, now there's something I needed to notice. I want to find here means I want to find what is probability that the number of women will be zero. Here, what is the probability that the number of women will be one? Here, what is the probability that the number of women will be two? Now, how are we going to know? Call this one men, call this one women. Okay, now take a look at this. The denominator is the same, it's 15, which is a possible numbers of ways of choosing two out of six using combinatorial analysis. But in the numerator, okay, if I have men, women, okay, we have three men. You know what this guy mean? I have three men, three women, but you know what this guy mean? I'm choosing zero from men and I'm choosing two, okay? Oh, sorry. That should be uh the other, it should be women, and I should have women first. Women, men. Okay, if I choose zero from women, automatically I will be choosing the other two from men. That is what this guy is saying. But for probability of women equal to one, I'm choosing one, one. I'm choosing one from men. I'm choosing one from women. And the probability of women equal to two, I'm choosing two from women. Then automatically going to choose zero from that. Now, do you know what I've been able to find here? Please pay attention. What I've been able to find. If you don't understand, ask question. So what I've been able to find here, okay, I've been able to find for each value of the random variable, for each value of the random variable 0, 1, 2, I've been able to find probability associated with it. That's what I've been able to find. Okay, for probability of 0, I have 1 over 5, probability of 1, 3 over 5, probability of 2, 1 over 5. And if I really want to know if I'm right, then I'm actually going to investigate if Komogorov axioms hold. Okay, if I say Komogorov axioms, okay, is each of these non-negative? Yes. What about normalization? Normalization is adding them up. Do they give 1? 1 over 5 plus 3 over 5 plus 1 over 5 has to give 1. Okay, and it does. Okay, that's what I find. Okay, that's what we've been able to find from the question. Now, I actually want to move right now. Now, when we're done like that, we need to present our result in terms of a table. This is a probability distribution now, okay? Which means, don't forget, y, okay? You know, if you take a look at this, a lowercase y, inside there, a lowercase y, but what I mean, the uppercase y, that is the random variable, okay, can take the value of 0, 1, and 2. That's exactly what I mean, okay? So right now, for every value of a random variable, we are able to find the probability associated with that. This is what we call probability distribution, okay? The probability distribution of a discrete random variable will enable you to see the likelihood of occurrence of that particular random variable. That's exactly what we mean. And you know what? For visualization, we can have a diagrammatical plotting of this. Okay. Now, the diagrammatical plotting of this is actually what we have right here. Okay, it's what we have here. This is what we call histogram. This is how histogram in statistics is generated. The histogram is generated, okay? The histogram is actually generated by plotting the probability associated with a random variable against the the values of the random variable. That's exactly what you're seeing here. Take a look at that. Okay, the one with the biggest bar will correspond to the biggest probability, which means, uh, you know, the probability that one woman will be selected is the highest if you look in terms of the bar. Is there any question about this? Is there any question about how we go from a probability distribution table to a diagrammatical way of visualizing it? Is there any question about that? You are good, right? Okay, now I'm going to move right now. Now, I'm actually moving. Okay, now take a look at, I want to go to another example. Of course, uh, where we talk about probability model in general, okay, that describe the possible outcome, okay, of a chance process. I told you probability model is a mathematical function to model, to depict, random phenomenon. How can we quantify random phenomenon? Okay, we use probability model for that. Now, I want to go into another example. And in this example, you know what we want to do? We want to start from experiments. From experiment, we're going to go to probability distribution. And from probability distribution, then we're actually going to go to histogram. Okay, now let's get started. Everything starts from experiments, because without experimenting, there is no way we're going to have outcome. Does that make sense? Now let's perform an experiment. Right now, the experiment is actually this. Consider tossing a fair coin 3 times. Consider tossing a fair coin 3 times. Then define X, the number of X obtained. I told you, the examiner will always disclose what is the characteristics of interest. That is the random variable ahead of time. Right now, okay, you are tossing a coin 3 times, but your focus is actually the numbers of heads. Now, I want to first guide you through that experiment. Please pay attention. I want to guide you through that experiment tossing a coin 3 times. Now, if I toss a coin 3 times, how am I going to know what the possibility is? I needed to pay attention. Okay, tossing a coin 3 times, if I want to go by way of Venn diagram, okay, tossing a coin 1 time, okay, I'm gonna have just head and tail. Okay, 2 times, okay, 2 times, head, tail, head, tail. 3 times, okay, 3 times, head, tail, head, tail, head, tail, head, tail. That is 3 times. Now, if I want to write my sample space now, okay, if I want to write my sample space now, it's going to be head, 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 tail, head, head, tail, okay, head, tail, head, okay, head, tail, tail, okay, tail, head, head, tail, head, tail, 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 head, tail, tail, tail. Look at that. How many do I have? That is a possibility. Okay. Now, this sample space is generated, you know, based because we're actually told the experiment is performed 3 times with a coin. Now, but I've defined my random variable in the question. They said it's going to be the number of heads. Okay. Now, if my random variable is numbers of heads, and because I perform experiment 3 times, my state space is going to be 1, 0, 1, 2, and 3. That will be my state space. So I mean I could have 0 head, 1 head, 2 head, 3 head. And let us now take a look. How many head here? 3. You know what I'm doing now? That's a random variable now. I'm assigning numerical values to elements in the sample space. These are elements. They are not figures. But right now, I'm assigning figures, Okay, now here 2, here 2, here 1. Okay, 2, 1, 1, and 0. Look at that. I'm done. Assign it out. Okay, now you can see here they all go from 0 to 3, but with different probability. Okay, 0 occur how many times? 1 out of 8. 1 occur how many times? 3 out of 8. 2 occur how many times? 3 out of 8. 3 occur how many times? And that is going to lead us, please pay attention. That is going to lead us to what we have here. Is there any question about, please pay attention, about this? That leads us to that. Okay? 0, tail. That's 0, right? Where we have 1 head. Can you see that? Where we have 2 head, where we have 3 head. Now, with that, then you will be ready now to produce a probability table. Okay? We want to produce a probability table. You start with the value. The value is X. Okay, the probability. This is the probability associated with that particular S that I'm talking about right now. Okay, when S is 0, 1 over 8, for 1, 3 over 8. Can you see that now? So from that, we're able to set up the table. Is there anyone who doesn't understand how the table is being set up? That's a probability distribution. Okay, now from the table now, we can produce an histogram. All what we just need to do is to have a diagrammatical plotting of the probability against the value. Is there any question? Is there any question about that? Any question? You see the way we went from performing experiment, okay, and to generating a probability table, and from probability table, we're able to sketch the histogram. Okay, now that's that. That's all we have for that. Okay, now I'm going to move right now. Of course, I think I've discussed all of that. Now, uh, I'm actually going to talk about the table. If you take a look at the table that we generated, okay, the sum of probability must be equal to 1. And each probability has to be non-negative, okay? Now, we actually want to generalize that, okay, if we have a table, generally a table is going to come in form of this, where we're going to have some values for the random variable, and we are going to have their corresponding, they're all going to have their corresponding probability. And of course, the probability has to be between 0 and 1. And not only that, the sum of probability has to be equal to 1. So what am I trying to remind you of? I'm trying to remind you of the common goal of axioms of probability function, that probability has to be non-negative. That should be, the sum of that has to be equal to 1. That's exactly what I mean. Okay, now I'm actually going to move right now. I'm going to move. Okay, now I just talked about from the probability distribution, we have set up a table. Is there any other statistical measure that we can have from the table? Yes, the statistical measure, we can talk about the average that we call the mean, which is also called the expected value. I want to figure out, I have a table, okay? I have a table, pay attention. I have a table. This is the table, okay? In the table, oh, give me 1 second. Okay, so in the table, if you take a look at this table right now, okay, I know the values of a random variable, and I know their corresponding probability. Can I figure out the average? And the answer is yes, we can do. How do we figure out the average? I will need to multiply a particular random variable by its probability. I'm going to multiply them out, then I'm going to add them up. That is exactly what I'm doing here. If you take a look at what we're doing here, This formula is telling us to figure out the mean of X. For instance, the other time, if you look at the question we solved about the numbers of women, okay, what if we want to figure out the average number of women? In a probabilistic world, we normally focus on the average. Okay, what would be the average? How do we find the average here? To find the average here, we multiply the value of a random variable by its corresponding probability. Okay, now that is a formula to use for that. Now I want to go into an example, and I need you to pay attention. Okay, I need you to pay attention. Give me 1 second. Let me drag this guy here. Now, please pay attention. Okay, a Babi's Apgar score is the sum of the rating on each of 5 scales, which give a whole number valued from 0 to 10. Okay, the random variable here is actually from 0 to 10. Now, if it is from 0 to 10, for each random variable, you have the corresponding probability. And the question is asking you compute the mean of the random variable X. Okay, interpret the value in the context. The mean of a random variable S is the same thing as expected value of a random variable S. Does that make sense? So what am I going to do in this regard? Okay, I'm actually going to use the formula. Okay, if you are submitting assignment or exam, make sure formula is very, very important. You can see here, I write the formula out before solving this. And this is my result. Is there anyone who doesn't understand how I figure it out? You multiply the random variable by its corresponding probability, then you add them up. Now, when you add them up, okay, the figure we have doesn't make sense until we interpret. We want to interpret this figure right now. Okay, the mean Apgar score of a randomly selected newborn is 8.128. So which is the average? Okay, for many, when you choose many of that randomly, okay, when you choose many babies that were born randomly, okay, that is going to be the average Apgar score. Any question about this? About how we find the mean? Now, let me tell you this. In a stochastic environment, because of variation, okay, we normally find the average. When something doesn't vary, if there's no variation, we don't need average. We need average because there's a variation. We need average because if I have different set of values, okay, I'm actually looking for probably the center of gravity. For, maybe I'm going to use that word that is used in physics. Okay, now let me tell you this. Statistics is like a story. When I find an average, I'm having this guy now as an average. Let me tell you this. What happened in reality could be less than average, could be greater than average. Does that make sense? What is going to happen if I take any, this very average was actually, we obtained that from the 1,000 babies that were born. Okay, there's possibility one of them could have a Apgar score greater than 8.128, and we could have some that have less than. And because of that, how can we trust this particular average? For us to be able to trust the average, then we need to be able to investigate the variance and understand deviation. The variance will actually tell us the degree of disparity, how the original Apgar scores of babies deviate from the average. Okay, now, and that is going to take us to another measure that we call measures of variation. Okay, and that is where we need a standard deviation and the variance. Now the question now is, okay, uh, you know, we find standard deviation, we find the variance, but before we first figure out the variance, then after figuring out the variance, what we need is the standard deviation. We find the square root of standard deviation. I'm going to tell you why standard deviation is preferred, okay, compared to variance. But right now, let's first figure out the variance. Okay, so if I have that table that we have the other time, a probability distribution table, and I want to find the variance. Okay, if I want to find the variance, I need to first find the average. Then I'm going to be, you know what I'm doing here? I will be subtracting the average from each score. I will square it, then I'll multiply by corresponding probability. That's exactly what I'm doing here. Is there anyone who doesn't understand what I'm doing in each of these? Okay, you find the average. Whatever you get from the average, you subtract the average because you are trying to measure the degree of disparity between the average and the respective score. Then we square that, we multiply by probability. Okay, that will give you the variance of S. Okay, now after getting the variance of S, then we find the square root of the variance of S, and that will give us standard deviation. But what is the difference between variance and standard deviation? I'm going to tell you right now. You're actually going to see that when we say variance, variance is in a square unit. But what about mean? Mean is not in a square unit, and that is why we need to find the square root of the variance. When you find the square root of a squared, it returns to the original scale, right? And that is why we normally use standard deviation as a measure of the expansion compared to the variance, because the standard deviation and the mean, they are on the same scale. Does that make sense? They are in the same units. Okay. Now let us now find the standard deviation. Okay, let's see how for the data set. You see what we're doing now? Please pay attention. Please pay attention. You see what we're doing now? We're using this formula now. You know, we found the average the other time. We got the average. What are we doing to the average? We subtract that average from 0. We square it. We multiply by their probability. That is what we're going to do forever. All the way here. Can you see that? Who doesn't understand? That's what we're doing here. Can you see that? That's what we're doing. You find the mean. The moment your mean is wrong, this is going to be wrong. Don't forget, you are just subtracting the mean from each observation. You're squaring that, you multiply by probability associated with that. That's exactly what you're doing. And at the end of the day, we found this to be the variance. Can you see the variance? Now, this variance is in a square unit. And if I actually want to find a measure of deviation, okay, that has to do with the average, with the mean, I have to use a measure that have the same units with the mean. Variance does not have the same unit with the mean. Because of that, I need to find the square roots of this, of the final answer. The square root of the variance is standard deviation. Okay, so can you see that? When I find the square root of this guy, that will give me this. Okay, now initially, okay, I needed to see the notation. This sigma squared. After finding the square root, then it becomes sigma. Can you see that? Sigma. Sigma. That is standard deviation. Sigma squared. That's the variance. Okay. Now, how do we now interpret this? Please pay attention. Interpretation matters. Okay. I needed to pay attention now. Okay. Take a look at the way we want to interpret that. Okay. You know, take a look at the way we want to interpret that. I said a randomly selected baby Apgar score will typically differ from the mean by what? By the number of standard deviation. Typically differ. I told you, okay, that very average, 8.128, okay, the APGAR score of some babies could be more than that average, could be less than that average. But what we're trying to tell the world, if it is going to be more than, it can be more than 1.4 or less than 1.4. Does that make sense? That's exactly what we're talking about. Okay. Is there any question before I move to the next objective? Now, do you know what we do today? That is going to be in the exam that you're going to write on Friday. The exam is going to start. I'm going to post the exam 8 a.m. on Friday. And the exam is going to be left open for 52 hours. But when you are not ready to start, don't start. Because that very exam is being programmed. Does that make sense? But on Thursday, I'm going to walk you through practice questions. I'm going to say I'm dedicating the class on Thursday for, a revision, where I tell you expectation. Now, you know what I've done today? I've been able to introduce you to discrete random variable. How do we figure out the probability associated with discrete random variable? How do we find the average of a discrete random variable? And how do we find the variance and the standard deviation? But you know what I want to do next, where I'm going now. And I want to talk about linear combination. I want to go into linear combination. Okay? I want to go into linear combination. I need you to pay attention. Now, let me tell you this. If x1, x2 up to xn, each of them, they are random variable, and they have a constant, a1, a2 up to an, and I want to combine them, this is what we call linear combination. Take a look at that. It means I have a new variable, y. Y is a linear combination of x1 up to xn. Now, if x is a random variable and y depend on x, y is also going to be a random variable. Now, from there, we can figure out what is the expected value, what is the mean of y, what is the variance of y, what is the standard deviation of y. Please, I need you to pay attention. Okay, now we're going to impose a theorem. For instance, if I have a linear combination that you have seen before, you've seen this guy before in high school, ax plus b, right? And x is a random variable, is such that the mean of x exists. Expected value of x is mu. Then expectation of as plus b or minus b is going to be this guy. And if I substitute, now I'm just getting because expected value of x is mu, so I'm going to have a mu plus or minus b. Take a look at that. A situation where mu equal to 0. What happened when mu equal to 0? Or when a equal to 0 here, then your expectation will be equal to b. Okay? And so like that, where b equal to 0, then you're going to have that. So that's just a theorem. Okay? That's just a theorem. Okay? Now, I'm actually going to move to theorem 3.2. And I need you to pay attention. Okay? Let x be a random variable with a probability distribution function x. And let g of a be a function of a random variable x. This guy here, when I say a function of a random variable x, this guy is a linear combination. G of s, a linear combination. How do I find the mean of a linear combination if I have a random variable? Now, this is what I'm trying to say. Please pay attention. Okay, this is what I'm trying to say. Okay, if y equal ax1, a1x1, a2x2, until you get to anxn, Okay, y is the same thing as g of x. Okay, now if a probability exists, if f of s, let's call this a probability function, a probability function exists. This is not a probability function. This g of s is this guy here. How do I find the expected value of y? How do I find the expected value of g of s? G of s is y. Now, if g of s is a discrete, then it's going to be summation, okay, the variable multiplied by the probability. That's exactly what we mean. You remember the other time, okay, please pay attention. You remember the other time, okay, if I have x, expected value of s is summation x f of s, right? But where y is a function, it's going to be taken as a random variable, which is exactly what I'm doing here. Now, if you pay attention to what I'm doing here, okay, this guy is situation where we're dealing with discrete. This week we're not dealing with continuous. So this is a situation for continuous. Okay. Now, let us now go into an example. Now, let x be a discrete random variable with the following. You can see they've give you table 0, 1, 2 with the probability function. Find expected value of g of x. Oh, what is the g of s? Oh, g of s is this. G of s is x minus 1 squared, x minus 1 all squared. We want to find the expected value of that. What am I going to do to find the expected value of that? Please pay attention. Okay. To find the expected value of that, what are you going to do? Okay. Don't forget g of s equal to that. What did I call the expected value of the g of s? Okay. Expected value of a g of s is that. Summation g of s f of s. What is my g of s giving? S minus 1 all squared multiplied by f of s. Now I need to first figure out this guy. And don't forget, you were given is 0, 1, and 2, right? You plug in 0. Do you see this? You plug in 0. You plug in 1. You plug in 2. Okay? Now, when you plug in that, why are you plugging 0, 1, 2? Because here, 1 second. Because here, what did they give you? 0, 1, 2. Can you see that? And they've given you f of s. So what you're going to do right now, okay, in evaluating that, what is f of 0? Oh, go to the table. When s equal to 0 is 10 over 28. F of 1, 15 over 28. F of 2, 3 over 28. Can you see now? That's what you're plugging in here. And at the end of the day, you have 10 over 28. So the mean, the expected value of g of s now is 10 over 28. Okay? If that is 10 over 28, now we have a rule. If x1, s2 up to xn, okay, are random variable and a1 up to an are constant, we can find the expectation of the linear combination. The constant is going to come out. A1, expected value of that, and so on like that. Then you're going to have that. Because I don't want to rush you, I'm going to continue from here tomorrow. But before you can read that, you'll be able to see. But I'm going to continue from there tomorrow because time is against me. Any question? Okay, be sure yours to say. Have a lovely day. Bye for now, everyone.